So this turbulent burning velocity that you see here for the thin reaction zone regime, so they are going to be estimated like this. So these are again empirical correlation. So since these are empirical correlations, it may change when you change the fuel, when you change their mixing parameters. So there will be a lot of other dependencies to that. So important factor which remains here is that the flame front would be looking like this. So if you look at the flame front in the turbulent flame structure, this is quite wrinkled. So once you have a quite wrinkled flame structure, then you kind of need to capture the flame front. So due to this turbulence or the eddies, the flame front gets wrinkled like this, what is shown here. These are the kind of a structure that you get to see. So idea how you track that. So one way to kind of track that flame front is that you can have isosurface of that flame front. So this G is in sort of an capturing that flame front on an isosurface basis. So this is known as G equation model. So I'll come talk about that in next couple of minutes, that the G equation models, which are also quite, so what it does, it actually tracks the flame front. That means if I have a turbulent flame front in a situation sitting here, then how the front moves and comes here. So every time one would like to track that flame front through this isosurface. So if one has to think about how I want to incorporate these things back in the computational approaches, then what are the requirements? So obviously one would like to use some sort of a reduced chemistry or tabulated chemistry, because if you try to capture even simple methane combustion can have more than 300 reactions. So if you want to go for all detailed chemistry in calculation, that's going to be quite expensive. Then how well we define this flame structure, then obviously taking care of this interaction between the turbulence and the flame structure, whether we need to go for statistical approach or things like that. So obviously, if you look this governing equations, which is the mass, momentum, energy, and the scalar transport equation, the unclosed terms are these terms. So there would be three terms. One would be reaction source term, one would be Reynolds stress term in the momentum equation. You'll have the turbulent scalar flux term. So all these unclosed term, you need to be closed. So I mean, now what we can do, each of these terms, we can see how we can close them using our displacement speed or the laminar flame speed. So already, just to recap that, there are models. This category of models can be applied to any sort of combustion. These are very specific to the premix flame, where we can have some sort of a flame speed closure, we can have the tracking of the flame front. So the first one that will come to that is the BML model. So BML model based on the Bray-Moss-Levy model. So these are the three scientists together they propose. So you define the progress variable, which I have talked about it, either in terms of non-dimensional temperature. So here U stands for unburned, B stands for burned. So that means if you have a flame front like this, so one side would be burned, one side would be unburned. So based on that, you can have the progress variable, or you can define based on the mass fraction. So then you can have a transport equation for the progress variable, and then you have some turbulent flux term sitting there and the chemical source term. Now the chemical source term, how would you like to? So here assumption is that when you talk about this particular model, it talks about very fast chemistry. So that means the flame size, which is quite smaller than the Kolmogorov size, but I mean, obviously smaller than the turbulent length scale or integral scale. So based on that, you define, okay, one side will be burned, other side is the unburned, and then you try to capture the flame front. But obviously, if there are some intermediate states, they cannot be captured. And how you do that, you said one side, so you sort of provide an, I mean, delta function, which takes care between a state of variable at C progress variable will vary between 0 and 1. So in between that, you will have this definition of the probability density function using the delta function. So what it does, so idea here is that you solve the transport equation and you can pre-compute the table, which we have talked about that. So once you have the pre-computed table of the flamelet library and things like that, so that pre-computed table actually you kind of use to estimate your temperatures and other things. So this is how you do that in between. So both the side you have burned and unburned side, you have the flame front which will pass through and you try to capture and the information. So here is the which I was talking about, the mean quantity, Fabry average mean quantity, and this joint PDF. So here again you use this PDF, the probability density function, but this probability density function, the idea, it's not you are solving the transported probability density function. So in I mean, as I said that you have these simple laminar flames. So the simple laminar flames, what you do, that simple laminar flames, these are the flamelets. So here across that you solve the species mass spectrum equation, and this equation, once obviously the right hand side the diffusion term is there, and once you solve this species mass transfer equation, you get the, so these are pre-computed situation. So this is pre-computed, and using a presumed shape probability density function. That means you are assuming what could be the shape of that, and then finally you define this particular function, and this function is used to estimate all your macroscopic variables. So with that you estimate these things back, you close this fluctuating component, and finally this is the term how you are going to close it. And once you close that term, then you are going to put it back. So obviously the flux terms, always we use this kind of counter gradient transport assumption, which is like this. So but this kind of can create troubles of some, I mean, sometimes, because this gradient diffusion approach, which for the I mean closure of this diffusive flux, we always use that hypothesis. But if there are counter gradient diffusion present, then this is going to be problem. But this is a very rare situation which may happen, but most of the time this gradient diffusion approximation is quite good, and you can carry on with that. And then finally what it leads to, that source term you kind of close like this. So it has an, you see the local unbound density, then the SL is your flame speed, and then you have this another flame surface density function which is estimated like this. So this is how in a simplified fashion you close that. This is one of the very simple model. And sometimes, I mean, now the question is that how do I go, am I going to get that flame surface density? Obviously this correlation shows how you can do that algebraically, or you can solve that transport equation for flame surface density like here it is shown. And once you do that and you see this turbulent transport and all this, so the underlying turbulent equations which are solved, they would be important. And once you do that, then you can kind of use them to close that particular source term, and which is used in. So the other approach is called the level set approach or G equations, which we are talking. So what G equation does is that it's actually try to capture the flame front. So using the information of your local burning velocity. So what it does that, how the flame front will move, like sometimes the flame front like this, sometimes the flame front would be like this, sometimes the flame front is like that. So at the different time instant, the flame changes shape. So here the idea is that you kind of going to track that flame front. So this is what you do. So to do that, obviously this is what the isosurface of the flame front that you kind of define. And then you have that equation for the isosurface. And the way it is done, that you say that on a particular flame front, this the material derivative is going to be 0, and that's how the tracking process takes place. And this is how the kinematics is given for that flame front, and this is the condition which is going to be satisfied. And finally you get the G equation, which is having a unsteady term, convection term, and the right hand side source term, which is closed like that. So that means in a reacting system, you are going to track that flame front using this isosurface. Idea is very simple. It is just like a surface that you have, and you just only, without bothering about too much, you just kind of track that surface so that you get that information. Obviously it can apply for the thin flames. You have a well-defined burning velocity, and you do not have problem with the diffusion term, and also if you are in the resume of corrugated flamelets, it can be used. So this has been used by a group in Georgia Tech quite a bit. I mean, then later on, it has been now commercially also available in your commercial CFD software. So one important problem which may arise here is that when the flame front across, I mean, especially rather complicated geometry, when you use this kind of a technique for multiprocessors and the flame front process boundary, then the tracking that flame front, I mean, basically define that G0 function may create a little bit of trouble, but there are sophisticated way. I mean, especially the sign distance function, what we are talking about, that has to be satisfied. So that sometimes makes life a little complicated, but nevertheless, this is quite popular in. And now, when you talk about this burning velocity, so which could be obviously the flame front is wrinkled due to turbulence and I mean other factor. So you can take into account the strain rate effect, curvature effect, the Lewis number effect. So all these can be provided in the modified burning velocity. So these are well-established correlations which are available. So idea is that whenever you try to kind of track that flame front, then you take into account the effect of the strain, effect of the curvature, burning Lewis number, and all these things. So now here, what you do that how you are going to, so this is kind of giving an idea in the particular flamelet. This is where the curvature is positive, this is curvature is negative. So all these informations are going to be taken into account in the burning velocity, and this burning velocity is going to be incorporated in your that G equation model. So that's how it's going to be done. Now, I mean, these are showing how the curvature is, I mean, influencing, and then finally your G equations which are modified based on these things. So that's how it's going to be modified. So now, so I mean, obviously, if you go to thin reaction zone resume, then there are certain issues which may pop up, which is like in the thin reaction zone, you have the small scale eddies which can penetrate through the premix heating zone. So preheating zone of the flame front. Also some transient of the flow would be there, nature of the flow. So the question is that, can this level set approach valid in the thin reaction zone resume? So assumption is that which we have provided in the inner reaction zone. So this is, if you look at the flame structure, so this is my reaction zone, this is my preheat zone, and obviously this is completely burned product, and this is, so this is this going to give me the flame thickness. So this is essentially my flame thickness. Obviously the flame thickness is quite small, that is what the thin reaction zone. So you can have some isosurface in terms of temperature. So idea is that you modified that G equations and take into account in terms of some temperature surface. So, and then your displacement speed is going to be modified based on your temperature. And then you calculate rest of the parameter, and then you solve the G equation model. So answer to that particular questions, if you go to thin reaction zone, yes, this particular model can be applied. But obviously, you have to do some sort of, or take into account some sort of a modification to those particular system and the equations. So once you take some kind of take care of some of these modification, then yes, this can be applied. So, I mean, in both resume, if you put it back, then that's how the final combined G equation would look like. Okay, and these are some of the order of magnitude analysis one can do. So typical for parameters range, where you can look at the Karlovich number, and so that we can kind of, okay. So idea is that when you go to, so this is my complete equation. So now this order of magnitude analysis shows that if you're thin reaction zone, then Karlovich number is going to be higher or greater than 1, then the curvature term is going to be dominant. Or if you are in the corrugated flamelet resin, then the Karlovich number is less, then the SL term is going to be dominant. So one case, this term is going to be dominant, other case, this is the term is going to be dominant. So, I mean, that is how the modification takes into account for both the resume. So that's why if you have a modified system, this works well for both resume. And now, yeah, that's, we can. So, I mean, we have both the equations, which is obviously the Fabre main equations and the variance equation for that isosurface. So that means whatever isosurface we are tracking, we can use the, I mean, can have a transport equation for the variance, and also we solve for that equation. So that way we can, once we do the, I mean, once we carry out the solution for the variation equation, this would include some of the effect of scalar dissipation rate and things like that, which are going to dictate how much the flame front is exposed to the strain and other stuff. So, I mean, if we obviously, in those terms, you will have the, this is one term, kinematic restoration term, then you have a scalar dissipation term, and which is kind of modeled using your information from the turbulent flow field, which is there as epsilon and K. So now that's kind of okay. So you introduce the turbulent burning velocity here. So finally, what it will lead that you will kind of modify the right hand side. You see that, and then this side should, I mean, don't worry about too much. So I mean, this is some of the correlation for the turbulent burning velocity, and graph shows how it varies. So these are again correlation based closure, but yeah, some of the, I mean, for a large section of flames, this actually work quite well. So yeah, we can kind of skip this portion. So now we come to some sort of an, when we talk about that, so those are the RANS context. Now if we go to LES situation, then how these things are going to be modified. So in LES, one can use this thickened flame dot progress variable kind of approach. But as I said, since the laminar, so LES you use, if you use some sort of an explicit filtering of the flow field, and the explicit filter size is delta, which is quite large than the flame front thickness. So idea is that if this is your filter size, if you see the box here, and this is my flame front size, which is shown here, you see this is going inside my filter size. So that means, which tells me immediately I won't be able to kind of capture that flame front effectively. So how you do that? So since the flame front is much thinner than my filter size or the grid size, then I won't be able to handle it. So what it says that, so there are two important things. What is there is that the, I mean, fundamental properties of this premix flame. One is the burning velocity, which is kind of proportional to my mass diffusion and the source term. Another is the flame thickness. So what you say that, okay, my flame front, I can thicken by a factor, an artificial factor, in such a way so that I would be able to resolve in my LES filter size. So that's the idea. So that I will kind of artificially, whatever my flame front thickness, for example, if this is delta L, then I will kind of multiply it with a factor called A. Now, point here is that, can I multiply the flame front artificial to just capture computationally arbitrarily? But I mean, the answer is no. But the way we do that, you kind of multiply the diffusivity parameter by a factor F, then at the same time, you reduce the reaction rate. So essentially this equation, what we talked about, that D3 you multiply by factor F, at the same time you take this one by a factor F, so prefactor. So that is how, so that means if you look at that, the laminar flame speed is not getting changed. But obviously what it does that, when you do, nothing is free of cost. When you do that kind of modification, the Damcoulomb number is going to be changed. So you see the Damcoulomb number is going to be also factored by a factor, I mean, or reduced by a factor A. So which means I have actually modified my flame front or thickened the flame front by a factor 8. So small eddies would not be able to interact with the flame front. So that kind of physics I'm going to compromise on. So this is not, I mean, theoretically or mathematically, this is consistent, but physically, if I look at from the physics point of view, then there are some inconsistencies. So what has happened is that through the DNA study, people have modified the equations and taken an extra function, which is called the E. This is called the wrinkling factor or some efficiency function. So you modify the things like an efficiency. I mean, you modify the whole thing with an efficiency function E. This efficiency function is going to kind of take into account the, and this, if you look at the efficiency function, it's a function of your fluctuating turbulent quantity, filter width, fact F, and delta L. So this efficiency function is going to take into account that artificial modification of the Dampoler number. So the modification is done, but it is done in such a way, and you incorporate some, and now of late there are research papers which can say that this efficiency function can also be evaluated dynamically. So that means once I evaluate this kind of factor dynamically, I would take into account the consideration of the flow field and things like that. So that's how the advantage it comes. So that means in LES, I mean, context, if you have this kind of thickened flame front, I mean, this is one approach which is also now available in commercial softwares, and so this allows you to capture this kind of premix flame. Now the other way one can do this kind of progress variable approach. I mean, we have already talked about that this progress variable you can use, where in terms of the progress variable could be defined, and then you solve that. And this is the subgrid scale. So the flame front displacement you close like this, and once you close like this, so this flame surface density is closed with an empirical relation. Now the subgrid scale wrinkling factor is estimated. So how it is estimated? So that is how you estimate that. Factor here. Okay. Now, so if you look at now the complete picture of this these things, the flame burning velocity. So you have this burning velocity. You have this burning velocity of DNS situation like this, and you can have in RAN situations how you can do like that here in the second one, and or you can have the situations like in the LES context, where you can have like this, which is going to give you the subgrid cell burning velocity. So in the RANs, obviously, we have seen this. So there would be consistency check to find out these velocities. And obviously, you can use some sort of a correlation-based model. This was given in the progress in energy and combustion science. So if someone is interested to look at a lot of this kind of research on combustion, then progress in energy and combustion, such, I mean, it provides you a good review, and you can kind of look at these things. So I mean, this is some of the picture where you talk about the issues when you have a different equivalence ratio, and so this is what more important from a premix flame. So I mean, now we move to that non-premix flame. So non-premix flame, the idea is totally different. What it happens is that if you have a reacting system like that, so one way you inject your fuel, you inject your oxidizer. So once they enter in the reacting system or the combustion chamber, they kind of mix through the molecular diffusion, then the reaction goes on. So the ideology behind or the models that are there behind the premix flame, they may not be easily, they cannot be straightforward to use for the non-premix flame. And this is a typical flame structure. So this is another experimental flame structure you see, and how, so this shows you the OH radical, here along the flame front. So this shows you nice canonical burner where, so you have a wide variety of applications. So most of the real life things where you see, like the conventional gas turbine, rocket engine, IC engine, gas turbine engine, diesel engine, not just aircraft engines, most of them are the non-premix in nature. So now when you go to even spray combustion, they are also pretty much non-premix combustion in nature. Especially if the sprays are injected in normal oxidizer situation like that. So what are important aspects for that? In a non-premix flame, issues which are going to be, there are issues which are more predominant. They are not the issues which one can see even in the premix case. So here mostly you look at the flame stability issues, what could be the flame shape, now the emission, combustion efficiency, these are the issue. Premix flame stability. So here what you do when you come to non-premix flame, so these are the again fundamentals of the basic non-premix flame. You define the mixer fraction. So mixer fraction gives you an idea, which is again a scalar. This scalar always gives you, you define that scalar value, again varies like your progress variable between 0 and 1. So 1, but here there is no bond or unbound situation. Here it's a pure air or pure fuel. So it varies between 0 to 1 between air and fuel, and you solve this mixture fraction equation. So once you solve that mixture fraction equation, then you define all your stoichiometric mixture fraction. So idea here is that you do not want to solve that species mass transfer equation, which is going to be much more stiffer and complicated, computationally expensive in doing so. So this is what you transform that equation. So these are some of the tables which are there in any fundamental combustion book, that if you have a fuel and oxidizer, then considering a single step reactions, you can find out the stoichiometric mixture fraction. So why stoichiometric mixture fraction is so important? Because any non-premix flame, when the fuel and oxidizer burn, they burn along the line or value where the stoichiometric mixture fraction, J would be at the stoichiometric mixture fraction. So there is where the reaction takes place. So for a given fuel and oxidizer, you can always theoretically estimate what is going to be my stoichiometric mixture fraction. Then you know, and a simple Bach-Schumann flame structure, this assuming there is, invert. So this is a case where one step, so fuel and oxidizer, giving you the product back, and it's an infinitely fast chemistry. So it means, so I have a, you see that here the fuel comes along the stoichiometric point where the complete fuel has come here, oxidizer has come here, along that you get a temperature rise. So that means wherever fuel and air come into the contact, it is, but this is a axis which is variation of the mixture fraction or the G variation. It varies from 0 to 1. 0 is my oxidizer, 1 is fuel. So they come and contact along the stoichiometric mixture fraction where the reaction takes place. But provided we have assumed this infinitely fast chemistry and you get the temperature peak. So it gives you an equilibrium line, and you can estimate at any given Z value, you can estimate what could be my temperature. You can estimate what could be my value of the fuel. You can estimate whether it will have any oxidizer or not. So that's the equilibrium condition. Now what it says that the structure, you have one fuel side situation and you have another oxidizer side situation, and from that curve, actually this is, you can find out what could be my temperature, what could be my other parameters. So, and what this equilibrium calculation provides you, this equilibrium calculation provides you an important information that any non-premix situation, this is going to be your, or this is going to be your calculation for theoretical temperature, what could be the maximum. So it get you an idea about the maximum possible temperature in a system. Obviously, I mean, that's what you call it, a adiabatic flame temperature, and theoretically you can estimate that. Now, if you have a reversible infinitely fast chemistry, that means you see that still fuel and oxidizer which are producing the product, but the product can dissociate back to fuel and oxidizer. You see this peak is not sharp anymore. So, but still the reaction is going on along the stoichiometric line. So you see, when you say in reversible and irreversible, the pattern changes, but still this provides you the equilibrium condition, and one can always estimate in the fuel side and the oxidizer side the different. Now, if you have irreversible infinitely fast chemistry, so now here you can compare. You see, this is what infinitely fast chemistry, and what happens if you have finite rate chemistry. So a finite rate chemistry cannot get you back that kind of sharpness in the temperature, whereas it always. And why the finite rate chemistry is going to be like that? I mean, clearly you can see the similarity between these kind of things, because there could be some sort of an situation or some product which are going to absorb some heat and things like that. Now, so here what you get an essentially a plot T versus Z or Z plot, and here the equilibrium condition. So you have irreversible reactions, you have reversible reaction. Either you can have fast chemistry or finite rate chemistry, and you see the line patterns. So particularly if you look at here, this is in the simple equilibrium pattern. Now here you get the reversible one, so you get some decrease in, I mean, here you come here, this is finite rate chemistry. Obviously the finite rate chemistry is going to behave, and there could be two possibilities: strain rate effect. The strain rate, I mean, if you have high strain or low strain, depending on that, you see that maximum possible temperature that you get. So given a fuel and oxidizer, you always can theoretically estimate what's going to be my maximum possible temperature. So even your actual reaction is going on in a reacting system, you may not be able to show. In a realistic situation, things are finite in nature. There could be irreversibility also. You may not be, I mean, some reactions could be, intermediate reactions could be reversible. So you may not get back the, I mean, you may not be able to reach the theoretical maximum theoretical possible temperature. So that's a check that you get. So idea here is that, so your species mass fraction and temperature, they are going to be now function of this variable Z or Z. So what it says, that this function, once I get, so very nicely, I mean, it will allow you to pre-compute the table, so which could be for some given state. And then when I solve the transport equations, I will get the information back for this species mass fraction and the temperature. So obviously you need to have some enthalpy to be calculated, because the enthalpy is going to be function of temperature. So that's very common in nature. So, and then you need the enthalpy of formation also, which will inform, I mean, having the information from the species mass fraction. So ideally, if you say that my enthalpy equation, if you say my Lewis number is 1, then these are the terms which are going to be eliminated. So once it eliminates it, you simplify the equation system to this one. So now what happens? I mean, if you try to find out the relationship between your enthalpy and mixture fraction, so this is what you get, the relationship between your enthalpy and mixture fraction. So here you see there is an inlet 1 and inlet 2. So one could be fuel, one could be, I mean, oxidizer, and then this could be outlet, and you find out this. So these are again simplified situations which allows you to carry out this exercise. Now that's what we talked about in the laminar situation. If you move to the situation where things are in turbulent, again the flame structure is going to be distorted. So you need Fabry average quantity of that. So instead of your, and then you get the variance of that. So in Rand's context, you will have density weighted mean, density weighted variance, and then you have the equations for the mean quantity, and obviously this unclosed term, which is closed as a gradient diffusion assumption, which, as I said, most of the flames or most of the time we do that. And this is what the final equation which will look like, which will take into account the information of turbulent diffusivity. So when you take into account the turbulent diffusivity, it's going to incorporate back your effect of turbulent into the system. And then how are you going to get that information? So I am solving for transport equation of Z, where in a boundary conditions where it is fuel or oxidizer, fuel it is 1, oxidizer is 0, then there would be at any point of time I will have some value of Z, and already I have said that this flame profile is going to be equilibrium, so I have this function which is available. Using that, the presumed PDF approach, I can estimate back my mean quantity. So if you see the correlation between this premix flame while using progress variable or G equations or the mixer fraction in non-premix case, the idea is pretty same. So you have a pre-computed flame structure. And why are we doing all this? I mean, the reason is that one can solve mass, momentum, continuity, and individual species mass transfer equation. So then you are fine. But when you try to solve individual species mass transfer equation, you have to solve for multiple species. So that's going to be computationally expensive. So to avoid that, we kind of transform the flame in a different space, like a progress variable space or mixer fraction space. And that space, from there, I will have a pre-computed situation. I would still solve the individual mass transfer equation, but that is pre-computed, so that during the runtime I don't have to do anything, and using some sort of a probability distribution function, I can estimate back by mean profile. Okay, so this is what you get for the final result. So this includes the effect of the turbulent, it includes the effect of the flame front and everything. Okay, so now what happens is that this is an, as I said, it's a presumed safe PDF, and that means my definition of the PDF or the calculation of PDF is done a priori. So before you start your actual computation, you have already done this calculation, and you solve these equations in turbulent flow field, and then every moment for a particular location and particular time based on your value of Z or Z, you estimate back your. And this is how some of these PDF function looks like. They are in terms of a beta function, which uses some kind of a variable. So this also pretty much known. This is how they look like. So that means when you pre-compute that table, this is done using this kind of function, and this has been taken care of and kept into the. Now this is in structure how the presumed safe PDF looks like, and you see the different location of the flame. This gives you an idea about idea about how you estimate this sort of PDF into the. Now if you look into the situation how we are actually solving the whole business. So here I am solving my Rand's equation, I have my turbulence equation. From here I send the information of the Z and Z variance. I have this PDF, and using this PDF, and I have this equilibrium calculation, so I get the temperature density back to the Rand's equation. So there is a connectivity between this my equilibrium flame structure to the actual calculation. So this is through the density. So that is the connection between that. Now, even if you non-premix combustion case, if you come, you can still do transport PDF approach. You can do this kind of flamelet approach. So I mean we can talk about essentially about a little bit of Lewis number. So Lewis number is an important factor which kind of comes into the mass transfer equation. And why it is important factor? Because it's kind of correlates between your mass diffusivity to thermal diffusivity. So for simplification, most of the time people use a unique or unit Lewis number. So the Lewis number effect is very important, so that you kind of do you neglect and then carry out the calculation. So here we try to construct the mixer fraction in the context of single stream chemistry. So it's essentially this is how the chemistry looks like. Then you have a mixer fraction, you do this. These are some they are in the any textbook if you look at it. So this is how you construct the mixer fraction. So you have two different stream and how you construct that. So that's not very critical to do. But if you have like a multiple species with the element, then this is what a formula which is given by Bilzer. One can use that to calculate the mixture fraction. If you have only one fuel and one oxidizer, single component and single element component, then it's very easy. But if it is not the case, then you have to use some sort of a slightly modified approach to calculate the mixture fraction. Without calculation of mixture fraction, you cannot use it in your so here again we try to calculate the mixture fraction in the context of two inlet. Yes, so here you see what you do that in an unburned situation, you take into account the, so this is called the you consider the mixture fraction calculations using those elemental information. Okay, so again coming back to this, so you have the you have the non-premix flame stack. This is what we have already talked about. We can skip that, and this is what we have done for also that you how your equations are kind of connected between. And yes, we can do this. So this also talked about. Okay, so now what happens is that why we talk about so much about mixture fraction, what we physically doing. Physically, I have a fuel and oxidizer, which is my Eulerian framework. From that Eulerian framework, I transform that flame to this mixture fraction space. So this is what we do, and this is what the transformation, and that's what so once you do that, you have the species mass transfer equations, and this is the term which will appear. Now this quantity is very important. This says that your Lewis number is 1. So this is the assumption that most of the time people use it. So now immediate questions could be, is this a valid assumption? For hydrocarbon fuel, it works well, but if you go to hydrogen based fuel, then this doesn't work, because hydrogen mass diffusivity is quite high. So that case, this will fall. And that is why these days, when you talk about the clean combustion and all this, the hydrogen combustion is so important. And why hydrogen combustion? One may think about, people have been studying hydrogen combustion for years, but this is where the challenge is. The capturing the film structure under turbulent combustion, your Lewis number, one assumption may not be valid anymore. So all this calculation pattern and things like that, that's going to be changed. So this is how you derive. So this is the equation that you solve as a pre-computed situation, and then you store it. So yes, this is what you solve with the steady flamelet, and then this is pre-computed and store it, and then you move forward with your, yes, this is what you do, counter flow assumption. Yeah, we can skip this portion. It's not important. Yes. So when you do this counter flow diffusion flame equation, it's obviously computationally much more less expensive. You get all the profiles for basis mass fraction, temperature. So, but these are done at the pre-calculation level. But obviously, Lewis number is assumed to be unity. So these are the problem what one has to take into account. So this is what you get the effect of the profile of the scalar dissipation rate, and this is how the profile of the scalar dissipation rate would look like, and this is at the stoichiometry. So this is nothing but your error function. So these are the all relationship available. Now another thing, what would happen when you do this counter flow diffusion film calculation in one-dimensional cases, one has to take into account the strain rate effect. Strain rate effect means when the flame is going to be extinguished. When you do that pre-computation of the table, then that time the taking care of that strain rate effect is important. Okay, and eventually this is going to give you a profile. So if you look at the immediately comparison to my equilibrium profile, I didn't have this parameter sitting there as a function. Apart from there, it was looking exactly same. So I have a y, which is a function of mixture fraction only, but in this case, now I am having a function which is also scalar dissipation rate. So that's the change that you bring in through this strain rate effect and all this. So this is much more realistic to capture the turbulent flame front. So once you do that, then obviously you need to, if it is not adiabatic, then you need to calculate the enthalpy loss. That means obviously between these two stream, what is the enthalpy loss? And once you take into account, that also become a function here. So the every moment when I solve the equation system, so obviously this is what I'm going to get back the mean profile. So there is no doubt about it that again I am going to use some kind of a presumed PDF shape and get back, but the differences would appear in other way around, that now whenever I come and solve my mixer fractions and variable for a given mixer fraction, so I have to look that function is going to be this profiles are going to be function of mixer fraction, scalar dissipation rate, stoichiometric scalar dissipation rate, and the enthalpy loss if it is not in adiabatic. So that function becomes little complicated. So these are another, I mean, you can see some function of the, okay, this is again the strain rate effect. So this is how you define your scalar dissipation rate. So there is a constant which is called the mixing constant or model constant. So these are for, I mean, most of the flame, this works fine as 2, but certain situations where you have partial pre-mixing or things like that, so this mixing constant of 2 doesn't work. So one has to be careful. As I said, always these models work for a large section of the flows or the flame, but there could be some exceptions where it is going to be failed for this constant. Otherwise, this is a quite, so what you show now in a Ram's constant, this is a strained laminar flamelet you have pre-computed. So the table will have a function of Z and stoichiometric, I mean, scalar dissipation rate, and you solve this Rand's equation, turbulence equation, you feed that information here, you calculate the scalar dissipation, you use this information, presume PDF and the PDF function using this, and using this, finally you get the mean temperature. So once you get the mean temperature, your density is sending back or sent back to the main flow calculation. So here you see you are only solving momentum, continuity, 2 more transport equation and the turbulence equation. So you are not solving individual mass transfer. That's why you segregate the problem and you reduce the stiffness of the system. So this is computationally quite effective. You can get results any quick turnaround time, but obviously anything you get. So these are some example. I mean, these are taken from paper. You can see how the flame structure look like. So this is using your flamelet model, and this is how the experimental structure look like. This is the quantitative comparison of the same. So in summary, flamelet based model where you solve for this mixture fraction variance and all this, these are flame normal analysis. So you first compute the flamelet equation. So this will provide you the profile as a function of mixture fraction across the normal to the flame. Then you solve the counterflow diffusion flame, and this function of the distance, equal diffusivity, those things you take into account. And in the turbulent flame front, you consider that during the analysis. Now, if you do the some little bit of comparison between flamelet, so this is what the flamelet I do. I solve the Rand's equation. I come here, use this profile which are known, and then finally get back my temperature based on this flame profile. The flame profile has been already pre-computed. But in transport PDF, what we do, if you talk about the scalar PDF, so this case in a flamelet model, we are also using this PDF, but these are, I mean, beta PDF. So the calculation of beta PDF is much more simpler, and it is done at the pre-computation table. So, I mean, calculation level. So we are not doing anything during runtime. But whereas in the transport PDF case, what we are doing, we are actually solving the transport equation during runtime using Monte Carlo technique. So here you have a Rand's equation, you have turbulence equation. This information comes here. Then you feed this information to the micro mixing model. Also, you feed this information to these Monte Carlo simulations where the transport PDF or the PDF functions are solved using particle-based method called the Monte Carlo. So this includes your mixing, this includes your chemistry, this includes your turbulent frequency, and finally it gives back me the density, which goes back there. So the calculation of this portion, this is expensive, because here I'm solving a transport PDF equation, which is not a presumed PDF situation. This is a transport PDF situation, but solving in a Lagrangian framework. This is a hybrid approach. This is Eulerian framework, and this portion is Lagrangian. So that means I am doing at the particle framework. Obviously, this is going to take a lot of time. Compared to flamelet, these are time consuming. Obviously, it will have some slightly better accuracy. It is applicable to different kind of flame zone. And that was the scalar PDF, but if you go to joint velocity scalar PDF, same thing. You solve this Monte Carlo technique. This is the Lagrangian approach. So this is the component which is going to take or most of the time of your system. So obviously, if you have some situation like equation for mean quantities are unclosed, so split the problem in mixing problem, mixer fraction, and you do the pre-computed local flame structure and using the scalar dissipation route. So that would take care of that portion. Second, if the turbulence can lead to a presence of more general flame structure, different flame profile, pre-computed flameless structure, extend the library for the pre-computed structure like the extinction flame, extinguishing flamelets, triple flames, things like that. So, or you can add this or introduce a new variable called the progress variable along with mixer fraction. That is called a different kind of approach, flamelet generated manifold. So FGM. That means my flame profiles are going to be function of not only mixer fraction or scalar dissipation rate, also progress variable. Or you can have model a joint PDF, things like that. So equation for mean quantities are unclosed. So using a description by probability density, this can be closed. Exact equation for PDFs are unclosed. I mean, you use some good micro mixing model. PDF equations when you are solving by finite method are costly. Yes, that's what you use particle based method. We use simplified chemistry so that you can get quick tabulations and things like that. So obviously when you go higher accuracy and things like that. So now the last one which I would like to touch upon, this is one of the another advanced model called the conditional moment closure. So here you have this instantaneous approach, I mean, balance equation and the unclosed term. So how you are going, I mean, you do that, you have this mixer fraction base. So this we have already talked about. Yes, we fast chemistry. So now you have exact and modeled equation. So either you can have equilibrium flamelet or you can have the strain flamelet. So that is what you do. This is where you use some sort of a mixer fraction based flamelet kind of equation. Now again you use the mixer fraction variance equations and things like that. So this is using your, you have exact equation for scalar. So you have a flamelet equation, you have the flamelet library, and then you have this, but you take into account with this based on the scalar dissipation rate. So this we already talked about. So this is called your GetC PDF. That means some sort of an FGM kind of approach. So you have a flame profile, which is going to be, so you have flamelet equation. So there is a flamelet generated manifold. So here you kind of, what you kind of do is that reaction source term for progress variable, and then you close the flow variable to close the flow variable to get back your these things. Now, as I said, the transport PDF equation, you solve those things using the particle based method. So obviously when you do that, it's going to be computationally expensive, but obviously then you may have some restriction using the chemistry, because if you go for detailed chemistry, it's again going to take a lot of time. Obviously storage retrieval of the parameters can lead to a problem. But also there are approach where you can have flamelet transported jet PDF kind of closure, where you can use some sort of an Monte Carlo based approach where you solve the transported PDF closure and then using some pre-computed library. So it's again a hybrid kind of approach where instead of solving everything in a situations in a Lagrangian framework, some of the pre-computed library you kind of merge with that. So that becomes a bit handy in a situation where your computational effort could be. Now coming to the conditional probability, so it's going to be again talking about like when you define that, so the your event when it is occurring for a between a particular interval. So they are conditional probability density function and the density, I mean the obviously density weighted function that you estimate like this. And then okay, so you get this function, so I keep this conditional mean. So here what you do that, you kind of get this conditional mean with the density weighted from that conditioned approach and the conditional fluctuation also. And then you have the correlation, and now you solve the transform the equation in the species transport equation in the mixer fraction space and solve that. And then when you solving that, this particular, I mean, here you can see the unsteady term when you kind of convert that in a space where it is varying with eta, and at the eta, so this you apply a simple chain rule to get that, and that at eta you try to find out that this thing, and finally you get the equation like that. So I'll come to quickly. Okay, so the finally for conditional mean you get this equation where this is going to be a conditional mean density, these are going to be a scalar dissipation rate, this term is going to give you the diffusion, I mean relate the diffusion to physical space, and this is the other one going to give you the relation between the conditional fluctuations. So then you get that the exact equation for conditional mean and all this you solve. So okay, so what you solve here is that you solve the exact equation for the scalar, and then you have mean mixer fraction, variance, and conditional moments. Then from the conditional moment and using the information from the again the PDF, finally you close the conditional moment closure approach. So this is I mean it was kind of been quite popular. Some of the research group, they have been actively pursuing this to solve that. But again, so this is an table from this review article where you can see where you have this presumed PDF situation and how you are going to close the reaction source term in a different way. So either you can have only function of mixer fraction or progress variable, or both mixer fraction and progress variable. So that's and CMC here, you with the condition you get this. So finally, and this is what you get in the transported PDF. So these tables are going to give you a complete idea when you use a different kind of approach. So okay, I'll stop here. So now if you have any questions, so I would like to clarify that. So you may post your questions or raise your hand. Any questions? Okay, so if there is no question, so what I would do, okay, Professor Sadiki, are you here? Yeah, it is visible.
Okay, thank you. So we will start today with the next part of our lecture. And for that, let me put it in presentation mode. So we will start with now this spray transport and interface coupling. I will perhaps try. So we have seen this yesterday and today. So I complete this by this modified correlation regarding the penetration length and also how to calculate it. And perhaps for people who are interested in, so there is also correlation for breakup lengths. I will send you that this presentation. Now we move to spray transport and interface coupling. It is the lecture number 9 and 11. We have introduced the statistical modeling for dispersed to phase flow. because we know that spray is a polydispersed system. Polydispersed means that the droplets have different properties of the size, the velocity, the temperature. And as we have seen yesterday, we have this structure or composition, so that to describe this, we need to deal with different processes like droplet breakup, droplet collision or coalescence, transport in physical space, the force acting on the droplet to make them moving, turbulence and mixing, mass transfer, heat transfer and combustion. That is the series of processes we will now try to capture and to describe. And for that, we have said that the spray polydispersity is characterized by droplet distribution function. And we could also reduce this description by providing some moments. And we have said that this distribution function is normally a function of the diameter, so the size, the position, the time, and we could also deduce some physical quantities, physical moment, but we can derive the different degree of moments. And this moment is provided by this, in which we need this function. And we have said that this function can be obtained by solving the evolution equation. It's evolution equation, which is called the Williams-Spray equation, in which we have this different term. This is the convective term, the time variation of this function. So we deal this here with the evaporation process, here with the force acting on the droplets, and we have here the temperature of the droplets, and we can also have some other dependency. And on the right side, we have so-called collision integral, in which we have a process like collision between different particles or droplets, coalescence, and so on. This means now, by solving this transport equation, so I think it is very time consuming, and there are in the literature idea to reduce this complexity by assuming a single phase description. But as we have seen, it is very, very restrictive to treat polydispersity of multiphase flow by assuming single phase description. If we do this, we cannot account for polydispersity itself and for different detailed microprocesses, like we have seen the modulation process, the the two-way coupling, the four-way coupling, etc. And this coupling occurs within each phase component. For example, we have coalescence, we have collision, or interface coupling. So we have seen that we can have the mass coupling, momentum coupling, energy coupling, entropy coupling, and so on. Like we, as I show you here, so we have this coupling, that is the interface coupling, and here we have also another kind of coupling that are the micro mixing. You say make it possible to investigate in details this type of coupling. And for that, we need different models. For example, dispersion model in this one-way coupling, modulation modeling in this part, and also collision and coalescence in the when we have four-way coupling, and in this two range as we defined them yesterday. we saw that if these parameters are very small, then we have one-way coupling. And if it is not very small, we can have what I said before. So we can have this four-way coupling, the two-way coupling, or one-way coupling, as we say this. And we could quantify this by including the volume, the particle volume fraction, or also we have also introduced the ratio of the interparticle spacing divided by the size of this particle. So this means if we solve this equation, so this means that we have to go to so-called separated flow view. This is the statistical, statistical method for numerical modeling of dispersed system, and it is not recommendable to consider that we can describe the multiphase system by assuming a single phase description. These are models which exist in the literature, but these assumption account or consider that there is equilibrium between the phase, so that they have the same velocity, the same temperature at each point, so that it is so-called a mixing control. And this can only be the case if we consider that we have small droplets, or we are in under supercritical conditions, so that there is no more distinction of different phases. And if we have small particles in which we say that the particle follow the flow, then we can say sometimes that, but it must be very, very delayed, so that we are in this one-way coupling. Otherwise, we have to solve this, and there are two ways to solve. I will not go into detail. I will show you after that, when I will introduce the Eulerian description in details. But we can solve this, and we can solve this in two ways: the Eulerian approach and the Lagrangian approach, in which we say we can follow the trajectory of particle. And here we say we can consider the particle as a continuum, or we can also try to consider the transported PDF, so the transported function as we had in this William equation. And if we couple them now to account for the coupling, then we have this multi-phase flow description, in which we can describe as at the microscopic level, we can try to resolve flows around the particle, and also to resolve the particle itself, in which we have the DNS of the dispersed system. It is very costly, and it is done only for single droplets. But we can go at the mesoscopic level. At this level, then, we can get the solution of this equation, the William equation, either following a Lagrangian procedure or a Eulerian procedure. In this one, we have then the Lagrangian approach for the solving of the William equation. We have the Eulerian approach, and if we have this, and we know that we have the gas phase, so the Fourier phase, and you have seen, I think, in the lecture with Professor Ashoke regarding the turbulence modeling. So we can describe the Fourier phase using runs or using alias. And if we do this, it is an Eulerian description of this flow. And if we have this Eulerian description of the flow, we doing this coupling, then we can do the Eulerian Lagrangian or Eulerian. And if we have this, we have the two kind of description we can do using rounds, using alias, or using also a combined rounds alias. If we use Eulerian Lagrangian approach, so this means that we we track the particle through the control volume in which is flowing by the Fourier phase, and here we consider both phases as continuum, and we have the Eulerian. So let's now focus on the Lagrangian description of our particle. We will also come to the Eulerian description later on. If we focus on the Lagrangian description, this means that we will follow the trajectory of our particle. And for that, we need the position of the particle, and we need also the velocity of the particle. So the position of the particle is given by this question here. This is the position of the particle derived by the time we obtain the velocity. And the variation of the velocity, let me say, the variation of the momentum is given by the sum of all forces acting on this particle. So if this particle has a possibility to rotate, then we have also this kinetic momentum as we have here, and we have the moment. We'll come back to this later. So different forces which can act on this particle, and this particle can also change its phase. Then we have, for example, heat transfer, and the heat transfer can produce different effects, condensation or evaporation. So modification of the mass here, and we have different forces. We can have, for example, gravity force, drag force, buoyancy force, but we will see everything in the next slide. And to make it very detailed, so we have here the question of motion, and we must also the transport equation describing further processes like a phase change, for example, the change of the mass here. So in the case of evaporation or condensation, so we introduced this yesterday, how to account for this effect. And if we consider a spherical particle, then we have the mass of the particle can be introduced here, and we can get the first idea how the diameter of the droplets can be changed during the time. And the temperature of the particle can also change due to the heat transfer input. And we can also solve this equation. We'll come back to this later. So if we take into account the forces which act on the particle, so the first idea for a mechanical engineer or for physicists, what is to do? So to consider that we have two groups of forces, so-called surface forces and volume forces. So the surface forces can be the pressure force or shear stress force. And here, an example, we have flow, and this flow act on the particle, so this particle experience forces around its surface, and the particle is represented by this control volume, and here we have the control surface. So we have the pressure force, is the pressure acting on the surface, and we know the expression, it is the pressure multiplied by surface element. And we have also the shear forces. We have the co-shear stress tensor, which act also on the surface, and these these can be transformed to get what we call the we have no, excuse me, we have the pressure and we have also the stress vector, and the stress vector can be, it is as forces, but we can relate this force to the corresponding tensor, and this is this tensor we have here, and we can do a transformation to put it in a control volume expression, going from the surface to the volume. We have the Gaussian expression, and we have this force can be transformed in this way. And here the same, the forces acting on the surface can also be transformed to a volume force, which acts here, and it is a gradient of the pressure due to the Gaussian expression. So we have this, and if we assume that the control volume is a constant, then we have this expression of the pressure force. And if we deal with gravitation force, then this can be related to this. And in this case, we can also write down this expression in this way if we assume that the volume is constant. But we can also have other forces like the drag force, what we know, if the particle is flowing, is in interaction with a flow which is uniform. So, and we have no acceleration, and we know that we have to deal with this drag force. And this drag force is provided by this expression of the surface. Let me show you. I think I have it somewhere here. So we have exactly this. You have the particle, it is flowing with this velocity, and we have homogeneous flow, and this particle experience a force which can be accelerating, and we call it a drag force. It can also be resisting, depending on the orientation of this velocity here. So the expression of the surface is this surface here, what we have in our expression in this formula. So having this, we can now try to put the forces which act on this particle. We have the pressure force, we can put this here together. That is this part. And we have also the drag force. It is this part. We can try to show, I think it is a good exercise for you to show how to come from here, to go from here to this expression. It is not a big issue. So we have also other kind of forces. So we have the virtual mass force. It is due to the change. We have a particle which is accelerated, and this acceleration change also the surrounding flow, and we have this relative acceleration here. Here we have the relative velocity, because it is a steady force, but this is time dependent. This is a small t, excuse me, and this is so-called Basel force. You take into account the retardation of the effect of the change around the layer, around the retardation of the change, the delay in the change of the layer around the particle. Here it is a volume force, like gravitation force. We have also other forces. I will show you them later. And here I put everything here together. We add the first one. It is a steady state drag force. And now here we have the so-called, we allow now acceleration of the relative velocity. Then we have the first one. The first one is due to the work required to change the kinetic energy around acting on the particle. And this, we have the kinetic energy and the work required to change the kinetic energy. It is this force multiplied by the velocity. This is the change of this kinetic energy. And from them, we can derive the virtual mass force. And if we account for the relative velocity, the change of the relative velocity with the time that is here, and the Bassett force, it is due to the delay in the development of the boundary layer around the particle. And we have this change, and it is an integration from the time. We can do from minus t to t, but here we put this from minus t to 0, and here we put it from 0 to t. So in an exercise, one can also, I will give you the exercise, one can try to show how we can derive this force. If we account for the initial velocity, then we have the initial velocity here at the time t is prime equal to 0. So here I show you the phenomena. When we have a body in accelerated, is accelerated through a fluid, there is a corresponding acceleration of the fluid around this body, which is an expensive of work done by the body. It is this work here done by the body, and this is the the first aspect. And we say this virtual mass account for the form drive to this acceleration, but the Bassett force account for the viscous effect, which introduce a temporal delay of the boundary layer development as the relative velocity change with time. Here, the relative acceleration, relative velocity changing with the time. We have the relative acceleration, and it is in the past, we have the delay. So this is integration from 0 to t. Here we have not, it is not an integration, but these account for this work required to change the kinetic energy, which is also an effect, a time dependent effect in which we have the relative velocity changing with the time. So the other forces are the so-called Safman force. They are kind of slip shear lift force. So we have our velocity, our particle is moving not in an homogeneous flow, but inhomogeneous flow. And in this kind, so is its experiential force, which is orthogonal to this. And we can obtain this expression in this form where we have the first part there. It is the relative velocity. And here, because of the effect, which is due to the inhomogeneity, we have the force which is orthogonal to this velocity, and we must have this vectorial product with omega, and this omega is only the rotational of this quantity here. And this is what we call the slip shear lift, and it is valid for higher particle Reynolds number. We have some coefficient here, the so-called lift coefficient. It is this expression obtained by some experiments, and we have dependency of Reynolds number, of the Reynolds number of the shear, and here we have the Reynolds number of the particle, and we have some correlation for this as we get, as it is also for the Sherwood number or Nusselt's number. So we have this and obtain from some experiment if this particular Reynolds number is more than 40 and here larger than 40, and the beta parameter is given by this ratio of these two Reynolds number. The first Reynolds number is known, and the other one, it is a function. We don't have here the velocity or relative velocity, but we have the rotation of the fluid. So the other force is the slip rotation lift force. It is so-called Magnus force. So we have the flow, and we have our particle, which is rotating. It is rotating, and due to this rotation and this interaction, so there is this lead to a force which is orthogonal also to this. And we have the rotation velocity. It is a constant rotation velocity of the particle. We have this here. It replaces what we had before, and we have the relative velocity, and we have also this expression. So how we derive this can be found in the book by Sommerfeld and also Chuji. But here I put only this for the lack of time. The particle rotation here, we have the particle rotation relative to the fluid. It is given by this expression. So we have, it is our our omega, what we had before. It is omega F minus this is particle rotation, or we can call this a relative particle rotation velocity. So the lift coefficients are given by this expression. So this lift coefficient, and we have two. This is the first group, which is given by Robin and Keller. And we have this one, which is normally used in what we use also. That is this expression. So we have then the list of different equations of different forces, and to put if we put them together, this was done by Bassett, Boussinesq, Jose, BBO equation, in which we have the change of the momentum of the particle is given by the sum of acting forces. We have the drag force, we have the pressure force or surface forces. We have here the virtual mass force. We have the Bassett force. We have the gravitation force. We have the Magnus force. We have also Bassett force, Safman force. We can also have Coulomb force also, like electromagnetic. There are a lot. And the question is, which forces are relevant in which configuration, in which situation? So this relevance, we try to derive them here, in which we write only these three forces. The other are related either to the rotation of the particle or to the inhomogeneous flow. We consider the very simple case with homogeneous forces, with homogeneous flow, but we can also extend them and add the other forces. So we have the drag force. We consider it for very small sphere moving through a viscous fluid, and this is the so-called the Stokes drag. We have our external force. This is the surface force. We have the virtual mass force, and we have here our Bassett force and body force, so gravitation. How to do this? So the idea is, or the objective is to transform this equation so that we are able to account for the effects which can allow us to quantify to say this force is necessary, is essential, or is important or relevant. So we consider the flow curvature effects are neglected. This means that we consider homogeneous, as I have said. So we we replaced this mass, or we can divide first by this mass and then replace it, in which we have considered that the volume here is, we have a spherical particle. If we do this, we obtain exactly this equation. So in which this term here, so we put it in the left, we move it in the left part, and this gives us 1 half and plus 1, and this is what we have here. Okay, and the other forces remain like they are, divided by m, and in the m we have replace the volume of particle by its expression. And if we do this, we obtain our response time, our particle relaxation time here, as we did it already. And we have divided by the density of the particle. Here we have the ratio between these two density, and here too. And here we have divided by m, we have only. Now we can say that this part, if we consider the Navier-Stokes equation, okay, this equation, Navier-Stokes, not only Navier-Stokes equation, we say we consider the momentum equation. We have the change in the fluid. We have the change of the momentum is the sum of all forces. We have the volume force and surface forces. And now we can replace this here by this part and this part. We introduce them in this equation at this place. We have first this quantity. This will go together with this one here, because this is u dot, and this one will go together with this, and we have this term, and for that we have this term. And we see that everywhere we have this quantity, the ratio of the density is the ratio of the density. And if for the case we had seen before where we calculate, we would like to characterize the spray, characterize the two-phase flow. So we say that this ratio is always small if we deal with gas particle, with gas solid particle or gas liquid particle. It is very small, and if it is very small, we can neglect this term here, so that in this case we have only the gravitation, the drag force, and the gravitation. That is why we see in the very different in various research papers, they say only that we use the gravitation force and the drag force. These assume normally that this quantity is very small. So this gives us an orientation how we can neglect these forces. But for large Reynolds number, where this part we say that the Reynolds number is not very huge, we say, or we see this also here, where we have derived this expression. We have said that we are in the Stokes flow region, and we say that the product of the drag coefficient divided by 24 and multiplied by a particular Reynolds number is almost equal to 1. So for large Reynolds number, so this Stokes equation, Stokes drag function should be modified a little bit, and we can introduce a factor here. And in this term, so it will come back to what we know as the drag coefficient, the drag force, what we use normally. And in this case also, we can modify everything. We put also here a constant which account for this large Reynolds number effect. For the Basel forces, we have also to introduce a factor so that in general, we get this expression where we have this coefficient here and this coefficient here. And also the same result will come out if this part is, if this term is very small. So we will only remain with this expression where the drag force and the gravitation force play a big role. So I remember you this effect here. We introduce dynamic relaxation time. We have also introduced the thermal relaxation time. We will come back to the thermal later on. I could not have time to translate this. Yeah, this is one exercise in which we consider here, I think you can follow me. So we consider this expression. This is what we obtain here at the end. Okay, this is exactly what we have here. It is the sum of the drag force and the gravitation force. The question is how we can solve this to obtain the velocity of the particle, assuming that the particle is has a velocity 0 at the time t equal to 0, and to obtain this expression as function of the relaxation time, as function of this quantity, which is u. And we assume that the velocity of the fluid is a constant velocity. If we get the velocity of the particle, we can also obtain the position of the particle, because in our Lagrangian formulation, so if we get this quantity, so we can then obtain the position. And if we obtain the position, then we can derive also the trajectory. And that is the exercise I give to you. Perhaps tomorrow I can show you the results. If you have also something, we will discuss with Professor Schocker how we can evaluate this if it is can be accounted for in your curriculum. So we have to evaluate or to calculate the position, and also to calculate the final velocity of the particle, in which we say that at this position, the velocity of the fluid is equal to 0. So we can also determine the case in which we have this velocity of the fluid, UF is equal to 0, and we don't consider the gravitation force. Okay, and then we have to make some approximation. But if we get this expression, we can also get this expression. So, but the big exercise, the main part is to solve this equation here and to provide the velocity of the particle as function of the relaxation time. If we know this, then we can use also these results for the next part of the lecture. I will show you the solution. The next exercise is to calculate this coupling. So we have this coupling parameter for the mass, for the momentum, and for the energy. So it was pi m, pi for momentum and for energy. And the question is, if we have an aerosol, it is a cold particle with this diameter, with this density, and we have air. It is air, its viscosity is given here. And we say that this aerosol and air are flowing through channel with this diameter here, and the velocity of this here, the velocity of the flow is almost 10 meters per second. And we say that we have the loading is given, it is equal to 1. If it is possible to calculate this parameter, please calculate them. And in this case, you can say in which case we have two-way coupling, one-way coupling, or four-way coupling. But if you want, I can translate it in German, in English. If it is, everything is clear, then you can start with this. I will send you this slide in this break time between 12:30 and 2:30. Let us now go into details on these expressions. I will focus first on the evolution of the drag coefficient. And this drag coefficient, so we call it either with D drag, or here I call it with W as in German, so Widerstand. So we have normally 3, I can say 4 origins for the evolution of the drag coefficient. And we see that here, if the Reynolds number is 5, we have to deal with non-rotating sphere. And if it is solid, we have normally 4 regions. The first one is the so-called, we are in the laminar region, okay, the so-called Stokes flow. And in this region, so we know that we had this expression as we calculate the relaxation time. It was calculated within this region here. We have also this region, it is transitional region. And we have the so-called Newtonian region, so-called turbulent one. And then we have the critical Reynolds range. And in this area, we have another behavior of this. And I classify everything here. First, up to 0.5 here. We can say if the particle Reynolds number is less than this, we have the Stokes or the crippling flow, and in this region CD is equal to this ratio, what I show you here. Okay, and we have seen also this in this expression we had before. So if we are between 0.5 and 10, and here, so we have the transitional region. CD decreases with an increase in the Reynolds number. And between this value here and the critical Reynolds number, it is the Newtonian region, and normally, so CD remain constant here in this region. And we can then speak for this Newtonian region, and we have these values. The value of this critical particle Reynolds number is between these two values. And around this value, the laminar boundary layer turns into the turbulent flow. I will show you now the pictures. And the separation point move forwards into the direction of the flow, and the value of this CD decreases. And after that, it decreases in the region which is called the critical Reynolds number. The turbulent boundary layer separates from the particle, what lead to a reduced value of this CD in comparison to the value in the Newtonian range. And that is what I am speaking about. So here, if the particle Reynolds number is very small, we have to deal with laminar, so it is also in German, excuse me. So it is a laminar flow. It is symmetric, as we see here. The flow flows around this particle in laminar way. And if we lie between the Reynolds number of particle lie between these two values, we have the building of the first vortices wake behind this particle, and between these two regions, so we have these vortices detached, and we have the so-called Kalman vorticity strict. And if the Reynolds number is very high, so there is the prediction of turbulence here, and very high, so we have full turbulent flow around, so behind these particles. And what we see here is exactly what we can see here for a stationary flow. And if we make averaging, so we obtain this. So that is what we get from this evolution here. And this is only to show that this is our the surface we are considering. And the particle is a sphere. So for high Mach number, we have different, we can see also incompressible flows. So we have also evolution of the drag coefficient as function of the Mach number. So we have for low Reynolds number, it is in this form. And for high Reynolds number, where shocks appear, so we have a large change of, we can say there is not really discontinuities, but we have a sharp augmentation of CD due to the shock which appear and which introduce an interaction between the flow and also the particle. So because there is also the presence of shock. People try in the past to do some correlations for this CD. And the most one, I will come back to the other, but I will put here general approximation. We'll also introduce the other in some application I will show you. But the general one is this one here by Morsi and Alexander in 1972. It is provided in this form as function of the Reynolds number of particle, and it is valid up to the Reynolds number of 50,000. This parameter, if A is what I call here A1, and B is A2, and C is A3. And we have these different values in for different range of Reynolds number. And if we compare, we introduce the thermal correction. So we will introduce this heat transfer number. And for that, we will see also later on how this heat transfer number look like. So I think it is time. I can stop here and we'll meet in the afternoon at 2:30. If there is questions, or please put them. Are there some questions? Yeah. Do you have some questions? I stop. And I wait for 2 minutes for questions because it is time. Otherwise, we meet in the afternoon.
Yeah, if you have anybody has any questions, please raise your hand or maybe type your question in the Q&A session.
But I can also put them in the afternoon.
Okay. Yeah. So, okay. So then we'll wind up this session then.
Okay, thank you.
Thank you.